We now take a look at a couple of try me problems. The first one, problem 5.8, involves a foldable tray for the paper supply of a photocopy machine. We're told the tray is supported by a single hinge at A and two slotted links, one on each side of the tray, and that if the paper weighs 20 newtons, we want to determine the reactions at the hinge and at point B for one of the links. Take a few minutes now to try this problem yourself. Resume playing when you're ready to see a solution. In looking at this figure, we have a couple of things competing for our attention. We have the tray itself, the paper on top of it, and the slotted links. The key issue in this case is actually going to be the slotted link, because if we look at that, it's pin supported at B and C, and there's no self-weight of BC or any other intermediate force, which tells us that that member BC is a two-force member. That is, the force that's supported by one of the links has a line of action that goes through B and C. That's not a very straight line, but what I'd like you to notice is that the vertical distance between B and C is 70 minus 25, or 45 millimeters. The horizontal distance between B and C is 60 millimeters. Those are obviously both multiples of 15 millimeters, and what that means is that this slope can be described as a 3, 4, 5 triangle. So we're going to know the orientation of the force transmitted by that slotted link, and we'll have essentially a single unknown pointing from B to C to represent that force. So in terms of the enveloping surface, what I'm going to do here is cut through the slotted link and the pin at A, and this is going to be my enveloping surface for essentially the tray, and then my free body diagram will look like this. So here's my tray. I've got a pin at A, so I'm going to have an AX and an AY. I've got my pin at B as part of my slotted link, and the problem statement tells me I've got a slotted link on either side of this tray. So we go into the plane of the screen, and on the other side of the tray is another slotted link. And so what I'm going to do is represent this as 2 FBC. So the 2 is there because I have two links on either side of the tray. And again, given the geometry, this is a 3, 4, 5 triangle. And then I have the weight at 20 newtons out here. So that's my free body diagram. And now I want to solve for, in the course of solving for this, if I solve for FBC, that will be the reaction force at one of the links. I've got three unknowns. I can write my three equilibrium equations. I'm going to choose to take moments about A because only the force transmitted by the slotted link will show up. And so I'm going to begin with that actually. So we'll say sum of the moments about A is equal to 0. And we'll just note that we'll break up this force into a horizontal component and a vertical component. Both of those components are exerting counterclockwise or positive moments about A. And so for the horizontal component, I've got 2 FBC times the cosine of that angle, which is just 4 over 5. And then the moment arm is 25 millimeters. So I've got 2 FBC. Cosine of that angle is 4 over 5 times the moment arm is 25 millimeters. And then I've got the vertical component, which is 2 FBC times the sine of that angle. And that moment arm is 60 millimeters. The only other force that's contributing a moment is the 20 Newton load, and we can see that that moment arm is 240 millimeters, so I have minus 20 newtons times 240 millimeters equals 0. So if I just rearrange that, I get FBC is equal to 20 newtons times 240 millimeters on the right-hand side. And then we're dividing by, first we'll just note here that I could divide 5 into 25, and the first term there is 4 times 5 times 2 is going to give me a 40. And the second term, I'm going to have 12 times 3 is 36 times 2 is 72. And that result is 42.86 newtons. So that is the force that's carried by one of those links. I can now just write force equilibrium in x and y to find the reactions AX and AY. Some of the forces in x equals 0 gives me AX minus the x component of the 2FBC, so that's minus 2FBC times cosine of that angle equals 0. And I can rearrange that to solve for AX as 8 over 5 times the force transmitted by BC, and that is 68.57 newtons. In the y direction, I have AY plus the vertical contribution from this force, which is 2FBC times the sine of the angle, 3/5, minus 20 newtons equals 0. And if I rearrange that, I get AY is 20 newtons minus 6/5 of FBC, and that gives me AY is equal to minus 31.43 newtons. So in this case, the AY component is actually going down. The AX and FBC forces are as represented in the original free body diagram. For our second try-me problem, we have problem 525. We have a body, a structure, ABCDE, which is a single rigid body, supported by a roller at D and a frictionless collar at A, that slides along this fixed bar FG. We want to determine the support reactions at points A and D. This is a symbolic problem, so we want to express the result in terms of parameters, the external loads P and Q, as well as the distances little a, little b, little c, etc. Take a few minutes to try this problem yourself, so pause the video and resume playing when you're ready to see a solution. So in this problem, our attention is directed at ABCDE. You can see in the figure it's a different color. That's what we're isolating. So I'm going to draw a closed surface around this. This is what we're going to draw for our free body diagram. And I will represent this schematically like this. So here's that little segment of the collar. Here's ABC. Here's CDE. And then here's the little segment that goes to roller D. I'll go ahead and add the external loads P and Q. And then we've got a roller support at D, so we'll have a single reaction force normal to that surface. And a key issue now in this problem is going to be to note that this is a frictionless collar at A. There's no resistance to sliding along FG. And so what that means is I'm going to have a single reaction force here, A, and this is going to make an angle of 30 degrees with the horizontal. And then I'm going to have a moment reaction because I'm not allowed any rotation of the collar. So my free body diagram now looks like this. I've got three unknown reactions, A, D, and the moment at A. My corresponding equilibrium equations will look like this. If I look at force equilibrium in X, I've got the X component of A, which is A cosine 30, and cosine 30 is root 3 over 2. So this is A root 3 over 2 minus D is equal to 0. In the vertical direction, I have the vertical component of A, which is A sine 30, that's A times a half. minus P minus Q is equal to 0. Finally, we have to pick a point about which to take moments. Here it's not so obvious what the best choice is. I could choose to take moments about this location because D goes through that location, but I'm still going to have the moment reaction of A and the two components, the X and Y components of force A that appear in that equation. So it's not really clear that that's such a great choice. I'm going to go ahead and take moments about A itself, so I'll take some of the moments about A. The force at A won't contribute anything. I'm still going to have two unknown reactions that appear in that equation. There's going to be the contribution from the force at D as well as the moment reaction at A. But it isn't clear to me that there's a really superior place about which to take moments that gives me just a single unknown in my equation. So I'm going to choose to take moments about A. If I do that, I have the moment reaction at A itself. Then I've got a contribution from P, which is clockwise and is through a moment arm of little a, so I have minus PA. I also have a clockwise moment contribution from Q, and that's through a moment arm of 2a. And then finally, I've got a contribution from D, and that's through little b. So I've got minus D times little b is equal to 0. Now in this case, I can solve for A first from the vertical equilibrium equation. It's presumed that I know these external loads P and Q. So I can see first from vertical equilibrium that A will be equal to 2 times P plus Q. And then I can take that result and substitute it into the horizontal equilibrium equation and get that D is equal to root 3 times P plus Q. So now knowing A and D, I can take that result and substitute it into the moment equation to get the moment reaction at A. And there I've got, moving things over to the right-hand side, I've got P times little a plus Q times 2a plus D now, which is root 3 quantity P plus Q times little b. And if I like, I can rearrange that just a little bit in terms of the external forces P and Q respectively. So I have I have the moment reaction at A is external force P times the distance A plus root 3b and plus Q times 2a plus root 3b.